All right, well, welcome everyone. I am JJ. Let's tackle an example problem. So again, we're just saying in this one, let's deal with distributed loads. Let's find the support reactions for our beam that we have here. So I have a trapezoid on this one. How we're going to work with that really isn't terrible for us, but we'll get to that in a bit. We know, though, to find support reactions, I'm going to apply equilibrium. Anytime I'm using equilibrium equations, I have to have a free body diagram. Just come in and get that drawn really quick. We'll come just right down below our beam, and I can stick it in just as a horizontal line. Should get me there. At A, I have a pin, so I should have an AY, and I should have an AX. At B, there's a roller. It's on horizontal ground. Rollers have one force perpendicular to whatever they're rolling on. Perpendicular to horizontal would be vertical. So I could put in a BY force over here at the far right edge. And then up on the top, I'm just going to replicate my distributed load. I start out tall on the left side of this and get smaller as I go over to the right in here, getting me something similar-ish to that. We'll show a handful of arrows coming down off of that, just making it obvious that it's a distributed load. On the left side, I'm at 20 pounds per foot is my height, so I get that labeled, 20 pounds per foot. And on the right side, it's dropped down to 12 pounds per foot. 12 pounds per foot. So to use this, I'm going to need to figure out two things. What's the area of a trapezoid? And where's my centroid of a trapezoid? We know our distributed loads act at the centroid. We know for a rectangle where that's at, just the dead center. I know for a triangle, that's a third of the way in from the 90-degree corner on it. For a trapezoid, that's a lot harder to find. We don't have that, really. We could look it up. It's a really complex formula. But there's better ways for this. Rather than trying to find the center of a trapezoid, I'm just going to say let's break this into two areas. So really, this is just a rectangle that has a triangle stacked up on top of it. My rectangle would have a height of 12, and the highest side of the triangle will be at a maximum of 20 in there. Again, we're really breaking this into area 1 is a rectangle, area 2 is a triangle. We should be able to work with that. So let's come in and jump in and go for that. So the first thing I could do, I have nothing else in the X. If I sum my forces in the X, even without knowing what to do with my distributed loads, I get the sum of the forces in the X is AX, and that should get me to 0. It's my only X force in here, which means my first answer can work out to be AX is 0. From here, though, I have AY and BY, two unknowns left in the Y direction. I'm going to have to do moments to find those. So let's sum moments at A. It'll get rid of AX, even though we know it's 0. It'll get rid of AY. BY would be our only unknown. So let's come in and do that. We'll take positive, goes counterclockwise. And I'm going to sum my moments up about point A. BY would cause a counterclockwise rotation. So plus, my distance here, I forgot to label, is 15. So 15, and that was in feet. So plus 15 BY. And then we'll go up and start getting my moments figured out here. For a rectangle, my distance should get to the very middle, and the force is just the area. Remember, for a distributed load, the force piece is always just whatever the area of a distributed load is. Shape 1 is a rectangle. This would cause a clockwise rotation, so minus, I need force and distance. So minus the area, the force, would be base times height. Base is 15. The height is 12. Minus base times height, that's force. Let's make that note in here. This is my force from distributed load 1. That's F1. And I can come in and say I need to multiply by my distance from A to the middle of shape 1. So times distance will be half of 15. 15 over 2, because that distributed load starts at A. We're just going to the middle of it. That would be D1, my distance to the centroid, or where that equivalent single force for a distributed load would be acting at. Then we also have a triangle in here. It would also cause a clockwise rotation, so minus, and again, we need force and distance on this. Force is area, So 1/2 on a triangle, 1/2 my base, 15, times my height. I don't want to say my height is 20. That's the height of the trapezoid. The first 12 pounds per foot went to the rectangle in here. So really my height should be 20 minus 12. That difference in here, 20 minus 12, it gave me just the height of the triangle piece in there. Or we could just put in 8. But times, that's my force, 1/2 base times height. I need to multiply by distance. So that's my F2. My distance for a triangular distributed load, I'm going to measure 1/3 of the way into the triangle from that 90-degree corner. For this one, the 90-degree corner is right at A, so I can just do 1/3 of the way in, 15 over 3. So times 15 over 3. Or times 5 would have gotten us there as well. That's our D for shape 2, D2. That's everything that would cause rotation. I can set this equal to 0. By is my only unknown in here. If I solve this, I'll get a positive, which means I guessed the right direction here. It works out to be By is 110 pounds, and it's going straight up, which would be my first answer. It's going up because I get a positive. I assume the right direction. All that I have left to find is AY then. I can just sum forces in the Y to get us there. Summing forces in the Y will be AY, my final unknown, plus BY, which I know is 110, plus 110, minus the area of each distributed load. So minus, for our shape 1, it is base times height, 15 times 12. Just like in our moment equation, that's just our F1. I don't have that extra distance in there because I'm not doing moments. I'm just taking the force. I just want area. I'm going to minus, because it points downwards, the area of the triangle. So minus 1/2 base is 15 times the height is 20 minus 12. Again, really the exact same thing I had up above. I just don't have that distance term in there to make it a moment. But that is F2. And that should get us to 0 equals 0. If I solve that for AY, I'm going to get my final answer is AY equals 130 pounds. I get a positive number from this equation, so my free body diagram, I guessed the right direction. Let's get that direction in here. We are going upwards. That'd be my final answer for that one. Hopefully this was useful. If it was, hit those like and subscribe buttons. Stick around, watch more videos. Let's get you an A with JJ.